one more example of being able to use functions as well as loops in some sort of example to help us with our MATLAB is being able to try to model Newton's law of cooling. And for those of you that have never taken differential equations, there's no need to actually take it. But we are going to utilize MATLAB to explore it a little bit. And so Newton's law of cooling basically states that the rate at which a temperature loses its heat in a steady temperature environment is proportional to the difference of the temperatures between the ambient temperature or the environment temperature as well as the object's temperature. So in other words, we have this differential, this first order differential equation. And for those of you that may have taken differential equations, this is a very common sort of differential that you would try to solve. And eventually it turns out to be the solution is this. So T, capital T is the temperature, lowercase t is the time. C is a constant as well as K, and K is going to be the constant of proportionality. We know that time is T, and Tm is called the ambient temperature. That's the temperature of the environment. Right? It doesn't matter what unit the temperature is in. So it could be Celsius or it could be Kelvin or Fahrenheit. But what we're going to do is we're going to be able to write some program that's able to kind of convert things and get everything into some sort of usable fashion. So just as an example, suppose that we have an object, it's initially 80 degrees Celsius, and then we immediately place it into an environment that's 20 degrees Celsius. After 2 minutes, the temperature becomes 60 degrees Celsius. And somebody that's a mathematician goes through, they've taken differential equations and they solve for the constant C, which becomes 60 degrees Celsius, and then the constant of proportionality K is going to be 1/2 ln of 2/3. So we have everything that we need to build this model at this point. All right, we're going to do a number of things here. We're going to prompt the user to be able to get these 4 inputs. Then we're going to write a function that's going to convert the Celsius to both Fahrenheit and Kelvin, and we're going to pass it back. We're going to create a row vector that's in increments of 0.1 minutes. We're going to compute the temperature time t of the jumper, and that should be of the object as a function of time over t. And we're going to print it. We're going to put it in a row vector, and these are the constants that you're going to input. And then we're going to print out 4 columns to an Excel file, all right? And we're going to title them appropriately. So we're going to have time and then 3 different units of temperature. Then we're going to print the temperature in Celsius. So we're going to need a loop to be able to do this. We're going to create a scatter plot, and we're going to label it, and then we're going to analyze it just slightly. All right, so it sounds like a lot to do, and it is, but really the code isn't too bad for this one. All right, let's just get the easy stuff done. Let's just get these 4 variables first. So we're going to, let's call it Tm, and that's going to be the ambient temperature. And we're going to input, so we're going to input the ambient temperature, and then we are going to get the temperature in Celsius, or actually we're going to get the constant of proportionality. So K, let's just say enter K, since not everybody knows what a constant of proportionality really means in this case. Okay. We're going to enter C, which is the other constant. So we're going to enter C. Okay. And then just like we did in the previous video, let's call time equal input, and let's go to say enter the time that the object is cooling. All right, so we got all that stuff. All right, let's create a row vector time t, and you probably remember that t has to be in increments of 0.01. Right, so we're going to say time is equal to 0, 0.1, just 0.1, not 0.01, and it's going to go up to time. And now we can go ahead and compute the temperature at time t. So time temperature t, and we're just using this formula. Right? So we're using this solution right here. So C e to the kt plus Tm. that's going to be equal to C times exp K dot times T, because remember, T is a row vector, so it's going to be a row operation, and plus the initial ambient temperature Tm. All right. So that's going to figure out all of the temperatures in Celsius. Okay, so that's going to be temperature at time T in Celsius. But that doesn't help us out to be able to get the Kelvin or the Fahrenheit. So now let's build our function. Right? So we're going to have a function, and we're going to pass back the Fahrenheit temperature, and we're going to pass back the Kelvin temperature. And let's just call it convert. I'm not sure if it's supposed to be named anything. Let's see what the instructions say. Write a function called convert. Okay. So convert, and we're just going to have the Celsius temperature, which is actually just going to be our capital T. So we're going to convert T, and we're going to have two functions. So Fahrenheit, and remember, Fahrenheit is 9/5 times the temperature. So it's going to be dot times temperature plus 32. So that's how we convert from Celsius to Fahrenheit. And then Kelvin's even easier. Kelvin's going to be T plus 273.15. All right. That's our function. That's easy. All right. So now let's go ahead and store the Fahrenheit. So I'm just going to say F comma K is going to be equal to convert T. And this is going to store the temps in Fahrenheit, F, and Kelvin. Right? At this point, I think we have everything necessary. Right? So we can go ahead and test this really quickly just to see if it works. And it might as well, so that way we don't have to sit here. And so I'm just going to go ahead, delete this, and I'm just going to type in, and the ambient temperature. Now remember, these are given to us. So the ambient temperature is 20, and then the constant C is 60, and the K is 1/2 ln of 2/3, and then the time, I'll just put in like 3 seconds, so that way it's not ridiculous, or even 1 second, just to see if this works. All right, so ambient's 20, K is over 1/2 times the natural log, and remember natural log in MATLAB is log 2/3, and the constant is 60, and let's just say 1. All right, and notice what it does is I didn't unsuppress capital T, right? But we do get the Fahrenheit temperatures, and we do get the Kelvin temperatures, and good for us that they are decreasing. All right, so notice that these are cooling off. It wouldn't be a good thing if Newton's law of cooling actually made them hotter. All right, so we're good so far. Now, the rest of this is being able to format it correctly. All right, so you might remember if we go down our checklist. All right, so we prompted the user, we have a function, we created a row vector, we computed the time of the temperature after time of the object T after time T, but now we have to print it out. Okay, so we're going to print everything to an Excel file. We're also going to print the Celsius temperature at each minute to the screen. Then we're going to make a scatter plot, and then we're going to do some analysis. All right, so let's go ahead and get it to our Excel file. So we have a header, and remember there are 4 columns. So the first one's going to be time, and the second one is going to be Celsius, and the third one's going to be Fahrenheit, and the last one is going to be Kelvin. All right, so those are our headers. And one other thing to remember is that these are all row vectors. All right, so F and K and T, which is actually the Celsius temperature, they're all row vectors. So we want to make sure that they're column vectors when we're done. All right, not a big deal. All right, remember the function XLSWrite, and there are 4 parameters. All right, so we need a file name, and before we do that, let's call. And I'm not sure if we were supposed to name it something specific, probably temps or something generic like that. It doesn't necessarily say, so I'm just going to call them temps, or let's just call it diff temp, so differential equations temp XLS. All right, and we are going to write to file name, and we are going to write the header. We're going to write it to sheet 1, and we're going to write it in cell A1. And then we're just going to do this a few more times. So we're going to XLSWrite, and so we had our time T. Now remember T, we have to be careful because that's a row vector. So we're going to say T prime to get it as a column vector. And we're going to put it in A2. And then we're going to have the temperature, T, and we're going to put that in B2 underneath the Celsius. And then we have our Fahrenheit, and we're going to put that in sheet 1, C2. And then finally, we have our Kelvin temperatures, and we are going to put those in, surprisingly, D2. All right, so let's go ahead and run this. And remember, ambient is 20, Kelvin was 1/2 times the natural log of 2/3. And then finally, we had C, which was 60, and the time. Let's just do something. I know it said something like 8, but let's just do 8. Okay. And if we did it correctly, there should be an Excel file that comes up over here. And it might take a moment because there's a lot of data to process. So it produced something. Let's just give it a moment. Let's open it up and see if we get anything nice. And I forgot to do the primes on these. All right, but it looks like it wrote it out, but I forgot to make C into T prime, etc. So it should run faster this time. So I should have done T prime to make this into a column vector, and F prime and K prime. All right, so let me run it one more time. Hopefully it doesn't take as long this time. And we'll open it up. And we're pretty close to done, by the way, so just hang tight. We're going to open outside MATLAB. And I did forget to do the fclose. This was the old file, so I'm going to delete all this stuff. We don't need that. So when I delete the old file, if I do an fclose, but here's all of our temperatures, which is really cool that we can see that it is indeed getting cooler as we go along. So I'm going to close this, and I don't think I can delete it. I'll give it a try. Oh, it did. Okay, that's nice. And I'm going to do a close F, and I'm going to do all. All right. What else do we need? So we've written everything out. We have to print out every minute. I think we had to do that. So we're going to go back, and we've done part D, which is the hardest part. We're going to print the temperature in Celsius to the screen at each minute. All right, so we're going to say for I equals 1 colon. We could just say time. So that's the time it's given, and we just want every minute. And we're going to f print f. We're going to say at %d or %f minute, the Celsius temperature is %F, right? And we're going to say I, comma, and remember this is a row vector t, right? So I'm going to call that ti. Right? And that should do it for that. We need a plot, so we're going to plot. I think it said we're going to plot the Celsius temperature over time. So we're going to point the temperature to the screen, create a scatter plot, and we're going to label it. So that's fine. So we're going to have time versus temperature. So we're going to have t comma t, and let's just do that. And we're going to just go ahead and say x label is going to be time, and we're going to have y label is going to be temperature in Celsius, and then title is going to be time versus temperature for Newton's law of cooling. All right, that's good enough. All right, so let's go ahead and run one last time, and hopefully we didn't do any sort of errors here. When I say we, I mean me. So ambient temperature is 20, and remember that's 1/2 times the log of 2/3, and C is 60, and let's see, since we're being specific, it says to do it for 15 minutes. So let's just say 15. All right, let's see if we get any errors. And remember, what was the F close? Close F. Let's give it another try. So apologies. This is 1/2 log of 2/3. And I forgot the multiplication symbol, so now it's just fatigue at this point. So 20, and then 0.5 times log of 2/3, and C was 60, and 15 was the time. All right, there we go. All right, so pretty cool, no pun intended there, but it looks like that it's starting to decrease here. And the question, I believe, was about how long would it take for it to get down to about 20 degrees, or the ambient temperature. So after 15 seconds, or 15 minutes in this case, it looks like it's not necessarily going to be what we want it to be. Oh, and right here, these are not correct. It looks like that these are not the right temperatures at 8 minutes, etc. And that's just because I believe that that's just what happens after every 0.1 seconds, etc. So this is really going to be, yeah, not at all what we want here. So let's just fix that up really quickly. So up here with our convert, we can go down here. We can actually probably recompute this. And if we wanted to, every minute. So T is 1, T is 2, T is 3. So let's just go ahead and recompute that. Or actually, we can just do it right in here. We could just copy this. That might be easier. So that way we don't have to sit there and mess around with it. So just copy it in here. And instead of T, we could just have I for the time in there. So that should work out pretty well. Okay. And we can get rid of that. We don't need that. And there was another thing that went on. We could probably suppress the close. So let's see what happens. So run it one last time. Ambient temperature is 20. Hopefully last time. 1/2 times log of 2/3. and Celsius, or the C is going to be 60 for us. And then this time, let's just do 30, because I don't think we used enough, we didn't use enough minutes to be able to get it to cool all the way, or at least what we wanted it to. All right, so this looks a little bit better. And so probably like right here at about 24 minutes, or maybe even here, because if you want to do the rounding correctly, and just round down to 20, because I think the last part of it was to ask, eventually the temperature of the object will become approximately 20 degrees Celsius. So we can use the graph. So let me pull up the graph. And the graph says probably somewhere like around, like right around here, around 25, 24, 23 minutes. It looks like it's becoming asymptotic at the 20 here. So if we really wanted to, we could just say around 20, 22, 23 minutes. But the rest of the stuff looks like it's good. So let's just go ahead and open this. Hopefully. Nope, it ran away. And my MATLAB crashed. Okay, so we're going to go with that. MATLAB crashed on me, but at least you can see that we were able to do everything necessary for this. All right, so hopefully that gives you a good overview as to how to utilize functions as well as being able to utilize loops in conjunction with a number of the other things that we've learned thus far in the course.